Okay, so what you have is a sample test. I just want to briefly tell you to read the instructions. Okay, high points of the instructions. Got to use only the Casio FX260 calculator. You can go over to the testing center, they'll loan you one so you can familiarize yourself with it sometime before you choose to take the test. I put the test in there yesterday. You need an ID. Now you don't get to take any notes in. Okay. There's no time limit. You got to take the test in one sitting. Okay. So among other things, don't drink a half gallon of coffee before you go in. Okay. And then there's a note for the testing center. Kind of an obsolete note back when I was teaching distance courses were being taken all over Virginia and other states too. But that's not happening anymore because Microsoft pulled an essential part of my whole system out from under me. And I thank them every day. Okay. Also because I prefer teaching in class. So. Your actions completely document your work. That means show all your steps and write out your thinking. Okay? The more you write out, the more partial credit you're likely to get if you need it. The more you show me, the more I can see about what you're thinking. And I'm not going to take credit away for something that you write. I mean, I'll take credit away for getting the wrong solution by the wrong method. But if you show me some insight in what you write, you might get a little bit of partial credit for that. If it turns out that you just made one wrong turn and everything else was right, you get a lot of partial credit. Okay. And it says undocumented and unjustified answers may be counted wrong. Don't just write down an answer. Taking a big chance. Show me how you got it. And if it's an answer that you could get by guessing, it's not going to get any credit at all. I have to see that you use the methods of the course in solving the problems, right? Okay, because you need to build on this. We're trying to build the mathematical foundation to use the ideas here, especially in subsequent courses. Okay. Numerical answer should be exact or appropriate. In other words, if it's a square root of 3, call it the square root of 3. But then you can say, okay, that's about 1.732, which it is. Okay. And you get that from the calculator because you're probably not going to remember. We just have to know the square root of 2 and square root of 3 because it came up a lot. We didn't want to have to go look it up on a table or do it on a slide rule. Slide rules are pretty neat, but calculators give you much more precision. Not that a lot of people necessarily know what to do with all that precision. Or when to cut it off. I've proofread this stuff pretty carefully. It's possible some problems might be missing important information. If so, now don't assume it's missing important information because you might not know. You might not just know what to do with the information that's there, right? So if you think it's missing essential information, you just can't go forward, make something up. Say, okay, if y is 17 then, okay? Things like that. And if it doesn't simplify the problem, if your assumption doesn't oversimplify the problem, you could get even full credit, especially if something's missing. If something really is missing, I'll throw out the problem. I just won't average it in. Okay? But don't assume you know when something is missing. And it says write one side of the paper only and staple test pages together. It's because I make copies and I don't want to decide on each test whether to make two-sided copies or not. Okay. So I just want one-sided copies. It uses up a little more paper, but it really kind of works better for everybody. Okay, now you got the problems. I asked you to put them into 3 columns. one column, you pretty much think you can get it, or you're very confident. Another category is you think you can get at least part of it, you know something about what's going on, but you're not sure of the whole thing. Okay. You're shaking. You think you have a shot, but you're shaking. The other is, you've never seen anything like this in your life. No. The other is, yeah, you've seen it. I hope you've seen it because we've been doing it for a month and a half. But you still don't know what the heck to do with it. Okay. So I can use that information. Remember that I spent all day Thursday and Friday, the first 2 days when we were closed, making videos and stuff to help you do this. Not that I'm going to accuse you of being ungrateful if you don't use it, but it's there. And I've talked about how to use it. So go back and look at previous class videos if you don't know what my recommendations are. But there are 4 levels: print, quick summary, less quick summary, and the whole blame thing. Okay. Go to whatever level you need. Now the test, I'm going to give you till next Thursday before class. I don't want you thinking about this test. I don't want you preparing for it past then, because there's other stuff that we're moving into that you got to pay attention to also. Okay. And I want you, the amnesty ends on Friday unless you, I might actually give you till Monday because it gives you the weekend to get all the assignments done on the half credit page. I emailed all the information you need for the half credit page yesterday. Did everybody get it? I know at least one of you emailed me and said, I can't get this thing to work. And there's probably a good reason for that. I did a time shift and didn't stop to think that it was shifting the due dates as well as, shifting the available dates as well as the due dates. That was my mental lapse. Okay. So I had to go through and manually change like 100 of these things. It doesn't take long for one, but you got to do it carefully to make sure you don't miss anything. Even at that, I'm pretty sure I did miss something. So if you still can't access something you need, email me right away. There's only probably 1 or 2 things, if that many, that haven't been done. Right. It only takes me a minute to do it if I know where to look. So tell me, I can't access this assignment. Okay. Tell me which assignment and which course it happened to be, like in the co-requisite course that meets before this one, or this one. I have to know which site to look at. Okay. So make sure you give me all the information. I can fix it quickly as soon as I see it. I won't be able to see things as quickly as I usually do until sometime Monday. Because it turns out that in addition to internet being out for a while, internet was fixed when I thought it was still out because I couldn't access it. It turns out my modem shows that time to die. It's not my modem, it's Comcast's modem. And I'm paying them every month to use. Okay. In addition to my bill. But it took them 2.5 hours with my wife yesterday to figure out the modem didn't work. It's going to take them till Monday to get there and install it. Okay. So I'm not going to have access unless I leave campus before I get it. Okay. So I won't be able to respond as quickly as usual, because usually even through the weekend I respond. Also, I'm probably not going to do much responding Friday or Saturday. Having a family thing, horse track in Kentucky. Kind of a big deal thing. It's kind of fun. Be more fun if I bet on the horses, but I don't know anything about horses, and I don't like to bet anyway. I would get a big thrill out of winning. I don't have any addiction toward betting. It's still kind of neat. So I'm going to drive 5 hours Friday, watch the horse race, come back later Saturday. So I probably won't be responding a lot. Okay. Can't assume I have internet access there. Okay, that's my status. Starting Monday, I should be able to respond quickly. But when I come back Sunday morning, try to catch up with everything. Okay. Okay. Now we're going to take a look at what's coming. As I said, more than half the class didn't get the assignment for today. That amnesty thing due to the half credit page, I'll transfer it to full credit, is good through last time on Monday. Okay, or not? Actually, it'd be class time. I don't want to give you that much. I want it by Monday. Actually, I want it by Sunday. Okay, I'll email you that. Okay. Now, what we're really into in this coming chapter is polynomials. I have a new favorite polynomial. Here it is. Everybody understand how to solve this? No. Although you could solve it for A. Because you got A squared here, and you got A here, and you got A here, and you got A squared here, and you got A here. It's a quadratic function in A. Okay? So you just put all the A squared terms together, and these other things all have numbers to go with, okay? They're just numbers. And to tell you a little bit about what this thing is, a kind of a miracle occurred in physics last week, a week before last. I didn't notice it, but the people I was explaining something to did, and it was pretty amazing. Okay, here I have what I call a beam. It's a piece of shelf standard. It's got a couple of magnets on the end, and it can be twirled around on the apparatus we have there, which is very low friction. You can see, can't see it on camera, but you can see if I start this thing, it's got to keep going for a while, a couple of minutes at least. Okay, it's not going that fast. Now, actually, I was going to say it's being twirled by a highly skilled majorette over there, but I can't show you a picture of her because the way she's dressed would offend family values. But no, that's not the case. There are no family values, are there? Okay. Anyhow, this thing was spinning. I gave it a spin. Now, if it spins fast enough, you can't see it necessarily. I guess I can tilt a little bit. I don't think there's a nickel. It's a nickel. It was a penny. But I guess I'm down to my last nickel, but I can't find my last penny. There's a nickel on the magnet. If it's spinning fast enough, it's going to spin that nickel off. Then that nickel's going to fly in a straight line and land on the tabletop. Well, I spun it. And I said, okay, we spin this thing. I spun it kind of fast. Okay. And I heard a clink. I didn't pay any attention. I said, it went into the cup. Doggone penny went into that cup. That seems like a minor miracle. Just randomly, it would go into that cup. It's never gone anywhere close to the distance of that cup, but I spun it pretty fast. Okay. Well, I've done a lot of analysis in this thing. Here's a picture. Things following the circular path, round and round. At some point, it left the path, went off tangent to the circle, and landed in the cup. Now, that was my assumption. I did some more analysis the other day and figured out that, whoa, it really didn't go tangent. So kind of here. But the thing is, if you do the physics of it, the so-called centrifugal force at the speed it would have to have is so great that it would have gone off far earlier. I mean, the thing would have had to been rotating. I can't show you in the major. I can't come on screen and do this. 1001, 1002, spinning 50% faster than that. It would have to be spinning 50% faster than that, according to all the physics that works. You can observe things and verify that it works with great certainty. It couldn't happen. Okay, you can figure out from this polynomial where it would have gone off, and from where it goes off, you just analyze quadratic function that gives you the projectile motion to determine how fast it had to be going to get there, which tells you how fast it had to be going around the circle, which is way too fast. It couldn't happen. Total contradiction. Now, I figured something out the other day, so I've got to work that in to see thing that I got gets it a little bit closer to that point, but it's still way too far. We have too much velocity. We'd have to test all kinds of things in lab to see if there's any possible explanation. Now, all that's just background. What really goes on here is summarized by this polynomial. Okay, this is a polynomial. Now, see this little unrecognizable symbol? That's a Greek letter that in our alphabet would be spelled xi. Okay, xi. You can replace that by x, and you have kind of a familiar looking x to the fourth, x to the third. Usually I don't inhale it, but it's really good. Okay, anyhow, you have an x squared here, an x here, and all the rest of this is just numbers. The a number is the radius of this circle. The y cup and x cup are just the coordinates of this point, where this is the origin. And on x, y coordinate system. I didn't want to call this x because we don't want to mix it up with this x or this x. Okay, too much x. And that's a fourth degree polynomial. You're going to learn about polynomials in this chapter. Okay. So when we finally get these numbers, I'm going to put it in the test and let you solve it. I'm just kidding. I'm not going to put that on the test. But theoretically, you could make a decent attempt at solving this thing. Okay. Now, and I kind of referred you to the MDE 61 videos because I'm going to go over this kind of fast. If you haven't had a chance to do the homework, you might need a slower, more detailed explanation. I'm going to give you a fast explanation. It'll give you maybe some idea of where we're headed, to give you some context. So first thing we did, we had a quiz, which I could have put in this class, to graph these two functions. Well, if you've done the homework, I remember you've got an amnesty. If you didn't do it, it's kind of okay, but it puts you a little behind right now, right? Yeah, wait things out as best it benefits you. We have this function here that you're asked to graph, and then this function. You can recognize these as the vertex forms polynomial. You can also recognize this as a horizontally shifted x being replaced by x minus 4, and vertically shifted y goes up 8, right? There's your horizontal vertical, that's x minus h squared plus 8 plus k. H is 4, k is 8. Meaning that you graph this thing, and here's the x equals 4 line, here's the y equals 8 line. You really want to start writing those lines out and understanding what they mean. If you're not doing it, it's because you don't understand the coordinate plane well enough to function properly in this course. You have to get that straight, okay? And that's one good way to start, because I've seen a lot of problems that people have understanding what graphs are telling, okay? Okay, well, anyhow. So, when I graph this thing, I just draw the x equals 4 line, the y equals 8 line. Now, you can get a lot of more detail if you look at the 160, the MDE 61 video, which is a lot slower than this one. I started by, first of all, finding the y-intercept. I plugged x equals 0 in because that's how you get the y-intercept, because the y-axis is the x equals 0 line. I plug x equals 0 in here, and I easily get y equals 24. So I know the graph has to go through this point. And I know the vertex has to be here. Well, that makes it pretty easy to draw. Now, I went into detail. Here's your toolkit quadratic function. Here's x equals -2, here's x equals 2, here's y equals 4, here's the x-axis. which is y equals 0. So right there, you got your 4x4 rectangle, right? You get the shape of the thing, and then you can imitate the shape thing over here. The scale is different because your 4x4 rectangle would be about here, and your red dot would be here. They should work to understand that. And I didn't talk about the red dot and the 4x4 rectangle in the MBE 61 because there are people from different pre-calculus classes there who don't talk about the red dot. So you're going to find the whole red dot rectangle thing, I think, useful as we get into polynomials. Anyhow, so there's the graph. Okay, you can use this graph to make estimates. You wouldn't get great estimates because that wasn't very symmetric. This side is a lot skinnier than this side. It's lopsided. It ain't a good parabola, but it kind of gives you the idea. Okay, so you can make a better parabola because you're looking straight at your graph, but I can't seem to adjust. Right. Okay, to do this one, we have a horizontal shift and a vertical shift and a vertical stretch. So we think of the fundamental toolkit functions, we stretch it vertically by a factor of 2. And that takes the point 2,4 up to 2,8 because the y coordinate of every point gets doubled. 2,4 goes to 2,8. Well, 2,4 goes to 2,8. Negative 2,4 goes to negative 2,8. 0, 0 stays where it is because you double the y coordinate, you still get 0. And then this dotted line gives you the shape. It's just a stretched out parabola. Now you should understand that quite well because you've had a lot of assignments on transformations and vertical stretches. We've been talking about it almost since the first day. Okay, it's one of the things that you're going to be able to need to do on the test. And we've made that clear for a couple of weeks now, 3 weeks probably. So anyhow, we do this thing. We see that the vertexes at HK, that's -3 and -5. Okay, so we draw x equals -3, y equals -5. Now first, we probably want to do the y-intercept because if we do the y equals -5 line first and find that the y-intercept is at 48, we don't have enough room in the top of our paper to put it on there, right? So get your y-intercept, your vertex, so you kind of know how to scale your page. Okay, so you need to know if you want to include the y vertex. Okay, well, the y vertex, the y-intercept. Okay, so anyhow, there we have it. We take a vertically stretched graph, we put the vertex there, the y-intercept there. That's what we're going to get. And then we estimate the zeros. Zeros, again, are the numbers that make this polynomial 0. And they coincide with the x-intercepts because the x-axis is where y equals 0. Well, we estimated -1 and -5. Well, you can plug -1 in here. You're going to get -1 plus 3, which is 2. Square that, you get 4. Double it, you get 8. Subtract 5, you get 3. You don't get 0. We get kind of a small number. 3 is not that big, okay, on the scale that we have here. So maybe -1 is kind of close. Now, if -1 is a 0, and the line x equals 3 is your axis of symmetry, well, then -1 is 2 units to the right of the axis of symmetry. So your other 0 has to be 2 units to the left. That would make it -5. You can check that out. You also get 3, you don't get 0. So how do you figure out what the zeros are? Well, to find the zeros, you have the formula for the function. If you let y equal 0, you get an equation that you can solve for x. So we write the x-intercept is y equals 0. So we set y equals 0. We get 0 equals 2 times the quantity x plus 3 squared minus 5. Okay. I did it more detailed and I'm going to talk about it here. I'll say it kind of quick, but right there is the equation. Same equation, I just switched the sides. Okay. Don't worry about y circle the 2, that comes up shortly. So we've got to solve that equation. First thing we want to do is add 5 to both sides. Now, some people want to subtract that 3. You can't subtract that 3. Get that out of your system. That 3 is tied up inside the square of something that has an x in it. Okay? That 3 is not a number you can operate on by adding or subtracting to both sides. The 5 is. It's in there all by itself. It's a term. 3 is not a term. This whole thing is a term. Okay. So you add 5 to both sides, and that moves the 5 over here. If there's an operation, then divide both sides by 2. That's going to be helpful. Okay. And you get x plus 3 squared equals 5 halves. Well, if something squared equals 5 halves, and then something is either 5 halves, square root of 5 halves, or the negative square root of 5 halves. That's something you should have known long before you came in here, but we've talked about it. Make sure you understand it. Okay. And then we can finish solving. We can subtract 3 from both sides. And we get x equals negative 3 plus or minus square root of 5 halves. And we can work that out. Square root of 5 halves is pretty close to 1.6. So that's going to be negative 3 plus 1.6, which is negative 1.4 instead of negative 1. And negative 3 minus 1.6 is minus 4.6, which is minus 4.6 instead of minus 5. So, negative 1, negative 5 are kind of close. For an estimate on a roughly drawn hand sketch graph, it's not bad. But, 1.4 and negative 4.6 are equally plausible. Okay. This is the exact form of solution. Okay. Now, another thing we could do, we could expand this thing. Now, by expand, I mean write out x plus 3 quantity squared expanded. That means write x plus 3 quantity squared as x plus 3 times x plus 3. I have this whole board. You can see what I'm pointing at. Okay. X plus 3 times x plus 3 by the distributive law. You're multiplying this x. Well, you multiply this x by the x plus 3. You multiply the 3 by the x plus 3. That's what I did here. And then you multiply the x by the x and the x by the 3 and add those. And the 3 by the x, multiply the 3 by 3 and add those. You get this. And you put the two 3x's together, give you 6x, you get x squared plus 6x plus 9, which is one of those special forms of a quadratic function that everybody at some point or another has had the prerequisites to this course has learned. But you might not have seen it for a few years. Okay, so you might have lost that. Again, the thing I keep emphasizing in this course is try to learn it so you don't lose it. You don't want to lose it before the test. You don't want to lose it before you take courses that depend on this. Okay? And you don't want to lose it before you take a course that assumes that you know the calculus. Okay. I don't know something about it at least. Okay, anyhow. So there it is. Now what do we do? Well, here's our equation, right? 2 times x plus 3 squared minus 5 equals 0. Well, we replace the x plus 3 squared by x squared plus 6x plus 9 because of what we got here. And we multiply everything by 2, we get this. And then we have an 18 minus 5 becomes 13. Here's the expanded form. This is called the general form of a quadratic. Okay, this is called the vertex form. As you know, if you've done the homework, I know not everybody probably has. Okay. So there it is. General form, vertex. Now we can solve this. We can use a quadratic formula. So we use a quadratic formula. If you don't know how to use a quadratic formula, do the assignments. Okay. It's real easy. You just got to remember the formula. You won't need it on the test. And often on the test, I'll write this much out. I'll write negative b plus or minus square b squared minus 4ac divided by 2a. You should know that that's what x equals in the quadratic formula. Okay. I won't write the whole thing out. I won't identify it as a quadratic formula. It's just an expression that I'm going to put there in case you forget it. But if you've used it as often as you're going to need to use it, to get the homework done, you're probably going to remember. You got a bad memory for this, okay, I'll put up the test. Yes, the field better memory than others. I used to have a better memory than I have right now. So we put the numbers into the quadratic formula and we simplify everything. We get -3 plus or minus the square root of 5/2, which totally agrees with what we got when we did this, which didn't require the quadratic formula. Okay. This is actually quicker and easier. But if you just give them this, they don't want to go to the trouble of putting it into this form. Quadratic form is handy. Okay. And you probably, if you don't have another reason to do it, don't want to go to the trouble of converting from this form to this form. But as you know, if you've done the homework, it's not hard to do that. All right. So that's kind of a synopsis of a lot of what you need to understand about quadratic functions. And we do quadratic functions as we move into the study of polynomials. I'm trying to think what I did next, give you this quick summary. Okay, that's probably it. Then we switch gears. We start talking about polynomials. Okay. Now that thing I showed you there with all the x side of the fourth, xi third, stuff like that, polynomial degree 3 in the variable side. Okay. Degree 4. Yes, that 4, I think it's degree consistency. Okay, here's a polynomial degree 3. Now let me also just say that when this is a polynomial degree 2. Okay, degree is just the highest power of x. So if it's degree 2, you have the quadratic formula. You can always solve it. There's also a formula for polynomials of degree 3 that people usually don't use because it's kind of complicated. Much more complicated than quadratic formula. You have 2 or 3 different things you have to evaluate together. It's hard to remember. But it does work. Okay. I'm going to use the name, P of x. Okay. Instead of f of x, P of x. Why P of x? Polynomial. Okay. So here it is. If we wanted to solve this thing, it would help be able to factor. Okay. Now I asked, well, what's a common factor? Is there some number that divides all the three coefficients, 8, -4, and 12? That's pretty obvious. Can you show me what that number would be? Okay, neighbors? Everybody see what number would divide all 3 of these? 2 would, wouldn't it? And 2 goes into 8, equal 8, 4, and 12, because those are even numbers, right? But you can get better than that. 4 goes into both of them, right? So you can write this as 4 times another polynomial, where 4 times this one has to equal 8x cubed. So this one would better be 2x cubed. And 4 times what would be -4x squared? Well, 4 times negative x squared, right? And 4 times what would equal 12x? Well, 4 times 3x equals 12x, right? So it's just distributive law, but we're kind of working backwards. And it's a very simple distributive law in this case. Okay. And then we can do better than that. There's also an x that's common to all these, right? So you could write 4x times 2x cubed minus x plus 3. Fair enough? That's pretty simple. So make sure you understand that. Because there's more complicated factoring that comes up in this chapter. Okay. And it comes up kind of soon. Okay. Now, if we wanted to solve P of x equals 0, if I wrote it this way and told you to solve it, you wouldn't know what to do. Okay. Now you have some clues about what you might do, in another week or 2. But right now, you probably don't have a clue what you would do with this. Well, what you have to do with it is factor it. And then Look here at this product I have. 7,342. I want you to work this out. 7,342 times 3,596 times 0 times 12. Tell me when you got the answer. Hold up your fingers. Well, the answer is 0. You know, you can multiply these in any order. What's 0 times 12? Well, we know that's 0, right? So now we have this times 0. Well, what's this times 0? Well, it's 0, right? So now we have this times 0 and that's 0. Now, if there's one factor of 0, if there's one 0 in a series of things you multiply, the whole blank thing is 0. Then we can also say, if there's any number in here, if there isn't a 0 in here, you're not going to get 0. Okay? The only way you get 0 from a product of 4 numbers is if at least one of them is 0. All right. Well, look at what we have here. We have the equation 4x times 2x squared minus x plus 3 equals 0. Okay. Now, what I said here, this looks kind of scary if you know what you're looking at, because you don't have a method to solve it. Quadratic formula doesn't work and it's not linear. So you can't get all the x's, you know, you can't isolate just a single x. Okay. But if you factor it, it's less scary. Why is it less scary? Because this times this is supposed to equal 0. It's actually this times this times this, 4 times x times this 2x squared minus x plus 3 is equal to 0. That means either 4 equals 0, which it doesn't, so we don't worry about it, right? Which leaves us x equals 0, or 2x squared minus x plus 3 equals 0, right? Okay. Well, this then is equivalent. I didn't even write the 4. I just wrote 4x equals 0. So the only way this product 4x times all this equals 0 is if 4x equals 0, which happens if x equals 0, right? Plug in x equals 0, and you got 4 times 0, which is 0, times whatever this is, and it doesn't matter what this is, okay? Because you're multiplying it by 0, it's going to give you 0. So either this equals 0 or this equals 0. Well, 4x equals 0 gives us x equals 0. 2x squared minus x plus 3 equals 0 gives us x equals, by the quadratic formula, you plug the numbers in and do what it says. They get 1/4 plus or minus the square root of negative 23. Well, that is a 0. But what's that tell you about the graph? Well, it actually tells you a little something, but it doesn't tell you a point where the graph crosses the x-axis. It does give you an x-intercept. Okay? It does give you an x-intercept, and the square root of negative 23 isn't a real number. It's not a number you can put on the x-axis. Okay? There's no number that you put on the x-axis that would equal, that when you square it would equal a negative. Any number on the x-axis squared is going to be positive, or if that's 0, you have to put the origin. You have to use the origin. So there it is. So we say that p of x equals 0 for x equals 0, or for x equals 1/4 plus or minus the square root of negative 23. X equals 1/4 plus or minus the square root of 23 ain't real numbers. Now, why do I say this ain't numbers? Because there are two numbers here, right? 1/4 plus the square root of negative 23 and 1/4 minus the square root of negative 23. Now, those are important numbers, but they're not helpful, at least not at the level of this course, for figuring out what the graph looks like. All right. So the graph of p of x passes through the x-axis only when y equals 0, and y equals 0 for numbers that you put on the x-axis. Y equals 0 only if x equals 0. That's what we get out of this. It's a very simple idea. Factor this thing, okay, if you can. Factor the thing Write the equation in factored form and hope you can solve for the zeros of the factors, okay? So each factor equal to 0. This factor equal to 0, this factor equal to 0. Had to put a couple of lines here. So that this splits off into this and this, and use what you have. That's going to be very important, this chapter. Okay. I'll be four. I do recommend you ponder everything I said. I'll go through the MDE 61 video. Set the tone for this whole chapter. Just a whole lot of the stuff we study in the chapters there. There is one other thing. Let's say P of X equals this is what we call the completely factored form of the original expression. Okay, we have this, we factored it to get this, and it is completely factored. Because you can't factor 2x squared minus x plus 3 with the real numbers. If you could, you'd have two factors whose product is 0. Okay. And if they're real factors, then each one is going to give you a 0, and there aren't any zeros from this term. And that's kind of what I say here. If it could be factored, it would give you real zeros, which it doesn't because we used the quadratic formula to prove that. So what we have is we've taken this function here and we've factored it into a linear function. Well, it's a number times a linear function, just y equals x. As a graph, it's a straight line through the origin, right? So we know 0, 0 is a point on that graph. Okay. And then times this, which is what we call an irreducible quadratic factor. That's equivalent to saying it doesn't have any real zeros. That's equivalent to saying the discriminant is negative. That square root of b squared minus 4ac thing is going to be the square root of a negative, and it's not a real number. The most fundamental thing in this chapter probably is the fundamental theorem of algebra. And it says that every polynomial factors into linear and irreducible quadratic factors. That doesn't mean you can find a way to factor it. You put numbers into this thing. If you know what A is, Y cup and X cup, then all you have is a number in front of xi to the fourth, number in front of xi cubed, number in front of xi squared, number in front of xi, and a number equal to 0. How are you going to factor that? Okay. Likely good is if I put the real numbers of that system there, and then you can sit down and up to just the major is getting tired. You can sit down and stop the world. Okay. And maybe somebody out there really thinks there's a bigger thing. You gotta accommodate your audience. Okay. And then they will worry she was getting tired. Okay. Well, right here is an example. Okay. You think you can factor that? Unlikely. I don't think I could factor that. I could approximate factors. There's a lot that I could do. I could probably prove that there is no way to exactly factor this thing. That we could actually get numbers out of it. Okay. So we have the question of how do you solve equations like this? That becomes important. You know, you probably don't have the driving curiosity I do about that system there. Okay. And this probably doesn't have a whole lot of interest for you, but there are other things that give you polynomials that might well in your future education career. Okay. So we have to learn a little bit about this. All right. Now, section 1, and let me pause for a second and double check. I'm sorry, without an internet connection, I'm even more clueless than usual. There's a lecture I would love to do because of all the chaos and turmoil the last couple of weeks. I might never get to do it. But what it comes down to, let's just take our polynomial, plus x cubed plus x cubed or 4x cubed. No, it was 8x minus 4x squared plus 12x. Okay. Has 0 at the origin. So I can begin to graph it. Right there is a 0 of an x-intercept. It's also the y-intercept. Okay, graph goes through this point. It's on the x-axis, so it's the x-intercept. Goes through the y-axis. It's on the y-axis, so it's the y-intercept, right? So we're done finding intercepts. Okay, now that's the only place that goes through the x-axis. Okay. The shape the y equals x cubed shape. With wiggles possible. Do the y-axis. Okay. As it will turn out, well, first of all, everybody remember what the x cubed shape looks like? Did it in the very first assignment of the math. Okay. It looks like this. I haven't shown you how to construct it, but it's constructed in a way very similar to the x squared graph. Okay, you just got to draw a lot more horizontal lines. So many, in fact, that you're going to have some invisible horizontal lines. So we'll do that. It looks like this. It flattens out for an instant. Right there in the very middle. Okay. This is the toolkit shape. Okay. The toolkit cubic shape with wiggles. I'll draw it over here. It kind of wiggles up and down like this. Okay. That's still a cubic shape with two wiggles. One wiggle, another wiggle. Wiggle down, then it has to wiggle back up. Okay. That's as many wiggles as you can have. And if it's a two-kit cubic shape, if you have any wiggles, you gotta have two. Okay. Now I can do some semi-wiggles, and we're not going to get into that right now, but that's kind of a picture. Now, the number of wiggles you can have depends on the degree of the polynomial, which is the highest exponent. If the degree is 3, you can have at most 2 wiggles. Okay. If the degree is 4, you could have 3 wiggles. Okay. And it would look like an x to the 4th graph. Okay. In this case, it's only got 1 0, doesn't have to wiggle much. Okay. So maybe it wiggles, maybe there's a wiggle down below the x-axis, maybe above the x-axis. But because of that x thing, it probably does something like this. Instead of wiggling, it doesn't completely flatten out. Okay. Now it's just plain old x cubed, it completely flattens out. But this here says maybe it doesn't completely flatten out and it goes through the order. Okay. And maybe it does something different. Sometimes you just got to make a guess. Just get a graph that looks about right. Okay, well, what if we look at the graph? Another is this. Okay. Can somebody give me a number? We look at this polynomial. Somebody give me a number that we could substitute for x in order to get 0. Show me with your fingers. What number could x be in order that we know this is going to be 0? No, if x is 0, it won't be. Okay, but let's take that suggestion. Well, then p of x equals p of 0, right? That means we just replace all those x's by zeros, which is going to give us 0 minus 2 times 0 plus 5 times 0 minus 7. Well, we multiply that out, and we get 70. Okay. So a couple people wanted to put up 0. Now, there's kind of a right thought that goes with that idea, but it's not that x equals 0, because if x equals 0, none of these are going to be 0, are they? And we want something that will give us 0. But if we put in 0, then you know the point 070 is on the graph, right? So we can already start making the graph for this. Here's your y equals 70 line, and there's the point of the graph. Now let's get back to what points does the graph go through, if any, on the x-axis. Okay, well, we know that it's going to go through some point of the x-axis. Its overall behavior is like this. It gets really big on this end, and it gets really big on this end, but big in the negative sense, right? You get big negative numbers if you go this way, and big positive numbers if you go this way. Except maybe if you flip it around the x-axis, then you have the big positives on the left, the big negatives on the right. Okay, flip that thing, or flip it upside down. Same idea. Okay. Now we know overall it's going to have this shape. So where are the zeros? Well, we took this suggestion x equals 0 and got some really good information. Okay. But it didn't give us 0. Why didn't it give us 0? Because we got three numbers here. -2, 5, and -7, and none of them were 0. The only way we're going to get zeros if at least one of those numbers is 0, right? So as I said before, this splits. If x minus 2 0, or x minus 5 equals 0, plus 5 equals 0, or x minus 7 equals 0. Can you solve those equations? Now give me a number that's going to make the whole thing 0. Okay, 2. 2 makes the whole thing 0. If you put 2 in here, you're going to get 0 times a couple other things. You don't even have to know what a couple other things are. You know it's going to be 0. Okay, give me another number. Okay, other than 2. Okay, 7. Okay, that's easy. If x is 7, then this is 0. In these numbers, doesn't matter if they're 0 or not. When you multiply it, it's going to give you 0. Okay, so we got 2 and 7. Okay, well, 7 is the biggest number we have up here. If x equals 7 here, x equals 2 going to be about here. Just a rough graph, but that looks about right. 2, 4, 6, 2 should have been a little smaller. No big deal. Oh, there's another number. What is it? Okay, you're going to have to put a negative in front of it. It's -5, right? That's like that bracket. Brace. Let's call it. Okay. Hard to call that. So, okay. There's your solution set for the equation P of x equals 7. I'll say for the equation P of x equals 0, your solution set is this. So we got to put -5 here, so it's maybe about here. And now we know we have points on the x-axis. Okay. Now, because the overall shape is the shape of the cubing function, it's either got to start low and end up high, or start high, come down here, flatten out, and end up low, right? But of course, it doesn't have to flatten out, it can move. Well, what that does then is the graph is going to look like this. It's going to come up way down here, and it's going to start to flatten out. It's going to, well, I've moved already. Okay, let's try again. As it turns out, they'll come up and down here. It's going to start curving a little bit. It's going to go up through this point. Probably going to go up above this point, come back down, go through this point, turn back around and come through this point. And that's badly drawn, partly because the chalk is really awful. And partly because my drawing is pretty long. I didn't want to go through the X here, but I probably should have. Probably should go up above Gotta go through this point, this point, this point, this point. It can wiggle at most twice. So there it is. Okay, I can do a better job, especially a better job for this trying to stick. It's kind of what's neat. I think it should probably come through with so. I'm not there. Take a little bit of graph. Okay. Now, do we know what the value is here? We could estimate it. That depends a lot on your ability to draw a good curve. And that's hard to do. It's hard, even hard for me to do. Okay. It's hard for me to get a good estimate. Now, if you use a little calculus, you can figure out what the x coordinate of the peak is here. Plug that into the function, find the y coordinate. You do the same thing for this low point, kind of like the vertex of the polynomial, or look up the quadratic parabola. Okay. So that's an overview of what you're going to learn in the first section. They're going to talk about far left and far right behavior, and they're not going to talk about this, which I think they should, because these are shapes that you should understand, that you need to understand. And they're going to just talk about put big numbers in. Well, big numbers work, but the reason they work is because you have this overall shape. So it's this overall shape that got wiggled close to the middle. And that tells you at the far left, the thing approaches negative infinity. At the far right, it approaches positive infinity. Okay, people typically don't have any problem with section 3.1. So I think you'll be okay. And then Thursday we'll talk about more stuff.